There's a line in the Grand Canyon where up to 1.2 billion years of Earth's history just vanishes. Below it, ancient basement rocks nearly 2 billion years old. Above it, younger Cambrian sandstone from shallow seas. Everything in between? Gone. No layers, no fossils, just a missing chunk of time big enough to hold the entire evolution of complex life. So what erased over a billion years from the rock record? The Great Unconformity is one of geology's strangest mysteries. A single boundary where younger rocks sit directly on top of much older ones, with hundreds of millions to over a billion years of missing rock between them. It's not a crack, it's not a fault line. It's where Earth's rock diary skips pages. The planet stopped writing, ripped out old chapters, or both, then started fresh on the same surface. In the Grand Canyon, that line separates flat-lying Cambrian sandstones deposited around 508 million years ago from basement rocks that formed roughly 1.7 to 1.8 billion years ago. At some locations, the National Park Service documents that about 1.2 billion years of local rock record isn't there. We're not talking about a little erosion. We're talking about an event, or series of events, that scraped away kilometers of crust across continents. The Great Unconformity isn't just a Grand Canyon curiosity. Geologists see similar massive time gaps across North America, parts of Australia, and other ancient continental cores. In the Grand Canyon, the classic version is where Tapete sandstone, part of the Tonto group, deposited around 508 million years ago, lies directly on top of the Vishnu basement complex, which formed roughly 1.7 to 1.8 billion years ago. That contact alone can represent anywhere from 500 million to over 1.2 billion years of missing record, depending on exactly where you stand in the canyon. The National Park Service describes multiple major unconformities in the canyon, not just one. There's the contact below the Tonto group, and the Great Angular Unconformity, where tilted older layers are cut off and buried by flatter younger ones. Same visual punch every time. Young rocks on old, with a gap that should feel impossible. Let's put real numbers on this. How do geologists estimate missing time? You compare the best age constraints for rocks just below the boundary and just above it. The National Park Service publishes a compiled list of best numeric ages for Grand Canyon rock units. The Tapete sandstone sits at around 508 million years. The Vishnu basement complex below it formed around 1.7 to 1.8 billion years ago. But here's the important nuance. Missing time is not one uniform number everywhere. The canyon contains multiple unconformities, and the size of the gap changes depending on which packages of rock are present at that exact location. In some spots, the missing interval is around 500 to 700 million years. In others, especially where Cambrian layers rest directly on ancient basement, it approaches or exceeds 1.2 billion years. Think of it as a family of big gaps with the same vibe, not one perfectly level knife cut. This isn't a quirky gap. It's a signature of something that reshaped entire crustal blocks on a planetary scale. One leading hypothesis ties this massive erosion to Snowball Earth, extreme glaciations in the Neoproterozoic, between about 720 and 635 million years ago. During those intervals, geological evidence suggests ice sheets reached low latitudes, potentially covering much of the planet. Glaciers are incredibly efficient rock removal machines. They strip weathered layers, carve valleys, and bulldoze sediment off continents and into surrounding basins. A 2019 study in PNAS argues the Great Unconformity is linked to unusually large-scale erosion during the late Neoproterozoic, with isotopic signals in zircons consistent with massive crustal removal and sediment recycling during that window. The mechanism is straightforward. Extreme global glaciation shaves the continents down to low-relief surfaces, then rising seas during the Cambrian drown those worn landscapes and deposit the shallow marine sands we now see above the unconformity. This model also lines up with the Cambrian explosion, the rapid diversification of complex animal life that shows up in rocks right above the Great Unconformity. But not everyone is convinced glaciers did all the work. Another camp points to tectonics and deep earth forces, the slow collision, breakup, and rearrangement of continents, plus changes in mantle support that can uplift crust far from plate edges. A 2023 study in Earth and Planetary Science Letters reports multi-kilometer exhumation across parts of the southern Canadian Shield, with timing extending well after the cryogenian Snowball Earth window. The authors argue the erosion pattern fits tectonic and geodynamic mechanisms better than glaciation as the primary driver, especially deep in continental interiors. In plain terms, uplift, changing mantle flow, and long-term erosion can also create huge missing sections of rock record. Not everywhere has to share the same cause. Recent work suggests both processes are involved: tectonic uplift and erosion near plate margins, plus intense glacial erosion in some regions during Snowball Earth. Unconformities are often composite, a surface that records multiple episodes of erosion at different times, stitched together into one boundary. So the Great Unconformity may be less a single catastrophic event and more a messy, planet-scale process that shaved continents down over a long and complicated history. This is where people get the Great Unconformity wrong. First, missing time doesn't mean nothing happened. It means rocks from that interval weren't preserved at that spot, or were later removed. The National Park Service explicitly warns against equating missing time with unknown events, or assuming the planet was dormant. Second, the gap isn't a uniform 1.0 billion years everywhere. In some spots, the missing interval is a few 100 million years. In others, especially where Cambrian layers rest directly on ancient basement, it can approach or exceed 1.2 billion years. Third, just because we call it the Great Unconformity doesn't mean it's one single event. Different parts of this boundary record different erosion stories at different times. So what's the hard evidence that this isn't just a neat line in one canyon? First, field geometry. You can trace the boundary where younger layers rest on much older rocks. You can see the physical cutoff that proves erosion happened before the younger layers were deposited. In some places, geologists can even map paleotopography, ancient hills and valleys carved into the older rocks that were later buried by younger sediments. Second, radiometric dating, especially using zircon minerals in both the older basement rocks and the sediments above. Those age measurements let geologists bracket exactly how much time is missing at different locations and show that similar gaps line up across multiple continents. Third, regional thermochronology, techniques that reconstruct burial and cooling histories of rocks. These studies show patterns of exhumation, rock removal, across wide areas, though the exact timing and cause are still debated. Global compilations of these surfaces show the Great Unconformity is widespread and clustered around late Precambrian and early Paleozoic time, lining up with known episodes of tectonic reorganization and cryogeny and glaciation. Even with all that evidence, there's still a lot we don't know. Researchers debate how much erosion happened before Snowball Earth, how much during the big glaciations, and how much after. Different regions show different timing, suggesting local tectonics and climate both mattered, and not every unconformity of this age fits neatly into a single global story. A 2022 exchange in PNAS argues that current thermochronologic data alone lack the resolving power to uniquely pin substantial erosion to the 717 to 635 million year snowball interval. In other words, the rock temperature data can tell us erosion happened, but not uniquely when within that broad window, so multiple timelines still fit. There are also open questions about how this massive erosion tied into ocean chemistry and the rise of complex life. Some studies suggest grinding down continents flooded the oceans with nutrients, possibly helping fuel the Cambrian explosion, but the details are still actively researched. So the Great Unconformity is less solved mystery and more ongoing investigation, with new data constantly nudging the story in different directions. Here's what can be said with confidence. If you could stand at the base of the Grand Canyon and run your hand across the Great Unconformity, you'd be touching a surface that marks hundreds of millions to over a billion years of lost pages in the local rock record. Below that surface are deep time stories of early continents, ancient mountain building, and long-buried rocks that formed almost 2 billion years ago. Above it, the record jumps forward to shallow seas that flooded a worn-down landscape, just before animal life exploded in diversity. Whether glaciers did most of the work, or tectonics, or both, the Great Unconformity clearly shows that Earth is not a quiet, slowly stacking layer cake. It's a planet that sometimes erases entire chapters before writing new ones on the same page. This isn't just a geologist's party trick. The Great Unconformity sits at the crossroads of tectonics, climate, and life. Understanding when and how it formed helps researchers test models of supercontinent breakup, Snowball Earth glaciations, long-term sea level change, and even the nutrient budgets that may have set the stage for complex animals. It shows how violently Earth can reset its surface, and how those resets can ripple out into the oceans and biosphere. That kind of insight matters if you care about planetary evolution, exoplanets, or just how fragile and dynamic a stable world really is. Next time you see a photo of the Grand Canyon, don't just look at the colors. Somewhere in those walls is a thin line where a billion years of local rock history simply isn't there. The rocks above and below still tell a story, but there's a whole erased chapter we're still trying to reconstruct. If you want more real mysteries like this, no conspiracies, just weird corners of actual Earth science, hit subscribe, and tell me in the comments, what other impossible features on the map should we dig into next?